So this was the proposition, right? Y is affine variety. Then you have two canonical ring. One is a coordinate ring and another is a ring of K algebras. So over K. K is algebraically closed. Then you have this AY I denoted, I think, right? This is nothing but KY, which I defined before, which is nothing but KX1, which is isomorphic to this KX1, X2, Xn modulo IY. And since Y is affine, you can assume this is a prime ideal. So this is isomorphic to ring of regular function. Right. And then you can, so if you take a point P in Y, then this corresponds to a maximal ideal Hilbert-Nurserin-Suss in your AY. Now you can talk about AY localization at MP, and you can also talk about OP or OPY if you want to include your Y. Then these two are isomorphic, right? So that is that. So of course, AY to your AY there is localization map, and similarly, and if you have a regular global function, OY to at the stock level you have a map, because this is after all some limit. So you just take this. If you take a regular function on Y, you just take the stock of F at P, right? So then this is isomorphic, and at the stock level, also at the local level, also they are isomorphic. So this was one, and then the third one was that Y is affine variety, so you can talk about the quotient of the, this is the integral domain. And now you have, for a variety, you can define what is called function field. That is defined, right? Which is a field. Now they are isomorphic. Right. So this was the proposition. So now tell me which one is proved and which one is not proved. If first one is proved, then second one is proved. Without second one.
First one you give it as step 2, step 3.
Oh, okay. So it will be something like this, that if you take AY, then AY will be, of course, inside OY, because after all it's a function on Y. And then OY, this will be inside OYP, because P belongs to Y. Yeah, because OY, every regular function, you can go to stock, and if it is non-zero, then it will be non-zero, right? At some point. And then this is nothing but AYMP. So first you prove 2. This isomorphism you prove. This is the first step. Sorry, not this one. First you prove this. This is easy. So this is step 1, I think, right? This is step 2. What is step 1? Step 1 is AY is sub of OY. Okay. Yeah. So this is step 2. And step 1, I think you prove this. This is step 1. Now this is the intersection of this, and this is now, because this is a domain, this is equal to AY. This is some standard result in commutative algebra. If you take a integral domain, then so now by sandwichness, AY sub of OY is sub of AY, and this is how you. And this is also this is easy. Everything follows from more or less definitions. So that's why probably I left as exercise. So this is also. So basically, quotient field of AY and quotient field of AY MP, they are same. This is also a right. If you take a domain and if you take a localization and take the quotient, that is again a domain, and the quotient field is again a. Okay, so let's continue with this. So let's go to the main theorem. So so if you have not done this, please complete the proof. Okay, this is the idea.